A rational function is a function that can be expressed as the ratio of two polynomial functions. So for example, if the function f of x is a rational function, it would be the quotient of two polynomial functions. Let's say function p of x divided by function q of x. And remember, division by zero is always undefined, so rational functions often have restrictions. The function in the denominator, q of x, can't be zero. And when looking at the graphs of different types of rational functions, you'll notice that there's lots of different shapes they can take. And you'll notice in these graphs, they often have different types of discontinuities, such as vertical asymptotes or holes in the graph. And those discontinuities happen at any x values that make the denominator of the rational function zero. So let me take you through the top 10 things you need to know about rational functions so that you fully understand the properties and graphs of all different types of rational functions. Must know number 1, simplifying and stating restrictions. Before we can start graphing rational functions, you have to be confident working with them algebraically and being able to simplify them and state any restrictions on the variable. And when we do this simplifying process, we're going to follow 2 steps. Step 1 is to factor the expressions that are in the numerator and denominator and then cancel any common factors. And then step 2 is to state any restrictions on the variable. And a restriction on the variable would be any value of the variable that makes the rational function undefined, which would be any value that makes the denominator of the rational function be zero. So let's look at 2 different rational functions. We'll simplify them and state any restrictions on the variables. For both of these rational functions, let's go ahead and try and simplify them and state any restrictions on the variable. Throughout the simplification process, you should always be looking if you can find any restrictions on the variable. A restriction would be a value of x that makes the function undefined, and the function would be undefined if the denominator is 0. Well, since the function in the denominator is a quadratic in standard form, it's tough to see what value of x would make it be 0. But if we factor it first, that'll make the restrictions more obvious. So let's go ahead and start this example 1 by factoring that quadratic that's in the denominator. I'll leave the numerator the same, and then this quadratic that's in the denominator, to factor it, I'll be looking for numbers that have a product of negative 18 and a sum of 3. The numbers that satisfy that product and sum are 6 and negative 3. So I know that quadratic would factor to x plus 6 times x minus 3. And now that the denominator is in factored form, it's easy to see what the restrictions on the variable would be. The rational function is undefined if the denominator is 0. Well, the denominator would be 0 if either of these 2 factors were 0. This factor of x plus 6 would be 0 if x was negative 6. So one of the restrictions on this rational function is that x cannot be negative 6. And then this second factor in the denominator also can't be 0 because that would make the whole denominator be 0. And what would make x minus 3 be 0 is if x was 3. So x can also not equal 3. If x was either of those 2 values, it would make the denominator be 0, and division by 0 is undefined. But now that I've stated restrictions and factored this rational function as much as possible, I can look for any common factors that cancel out. Well, I notice I have a factor of x minus 3 in the numerator and in the denominator. Anything divided by itself is 1, so I can cancel those factors out. X minus 3 divided by x minus 3 is 1, which means this rational function simplifies to 1 over x plus 6. And then I have to make sure I state those restrictions on the variable x again. X still can't equal negative 6 or 3. And stating these restrictions is not only important so that we know when this function is undefined, but it's also important so that we're actually able to state that this function is equal to this function. Because if you were to sub 3 into this function, you would get 0 over 0, which is undefined. But if you sub it into this function, you get 1 over 9. But since we've said x cannot be equal to 3, subbing in any other x value other than 3 into these 2 functions, you get the exact same value. So having this restriction here allows us to state that it's equivalent. And as we go through this video, we'll talk about graphically how these discontinuities show up on the graph of a rational function, but we'll get there. So let's practice one more. Let's do example 2, where we simplify that and state its restrictions as well. Once again, the first thing we should do would be to factor the functions that are in the numerator and denominator. That way we'll be able to see if any common factors cancel, and also we'll be able to see any restrictions on the variable. Well, in the numerator, there's a difference of squares. It's an x squared minus a 3 squared. So that would factor to x minus 3 times x plus 3. And in the denominator, there is a quadratic trinomial, so I'll find numbers that have a product of 12 and a sum of 7. The numbers that satisfy that product and sum are 4 and 3, which means the quadratic in the denominator factors to x plus 4 multiplied by x plus 3. And now that the denominator is in factored form, I can easily see the restrictions on the variable. What would make that denominator be 0? Well, the denominator would be 0 if either of these factors were 0. And x plus 4 would be 0 if x was negative 4, so that's one restriction on the variable. And x plus 3 would be 0 if x was negative 3, so that's another restriction on the variable. And now I should check if any common factors cancel out. I notice both in the numerator and denominator, there are factors of x plus 3 that can cancel out, because x plus 3 divided by x plus 3 is 1. Which means, as long as x does not equal negative 4 and negative 3, this rational function would be equal to the version where those factors of x plus 3 are canceled. It's equal to just x minus 3 over x plus 4. And then I make sure to state the restrictions on the variable x again. X cannot be negative 4 or negative 3. Must know number 2. Operations with rational expressions. Let's start with how to multiply rational expressions. Anytime there's an operation between rational expressions, the goal is to find a simplified answer and also state the restrictions on the variable. So the first thing you want to do that's going to help with the simplification and with the stating of restrictions is to check and see if anything is factorable in either rational expression. Notice this quadratic trinomial can be factored. It can be factored to x plus 3 times x plus 1. And now that the denominators are in factored form, it would be easy to see the restrictions on the variable. Since division by 0 is undefined, this product would be undefined if any of the factors in the denominators were 0. Well, 2x would be 0 if x was 0, x plus 3 would be 0 if x was negative 3, and x plus 1 would be 0 if x was negative 1. So those are the restrictions on the variable. And now we can work on further simplifying this product. When multiplying rational expressions, we are allowed to cross-reduce factors, meaning we could cancel a factor that's in a numerator of one rational expression with a factor that's in the denominator of the other rational expression. Or we could combine these fractions first and then cancel factors. I think I'll do that, because when multiplying fractions, it's equal to the product of the numerators divided by the product of the denominators. And now I'll do my canceling of factors. These factors of x plus 1 can cancel. Since something divided by itself is 1, we can cancel those out. And also, there's a factor of x in both the numerator and denominator, so those can be canceled as well. And on each line of my simplification, I should keep writing the restrictions. And now I can write my final simplified answer. Notice in the numerator, I'm just left with 3, and in the denominator, I'm left with 2 times x plus 3. And then it's important the restrictions are written again. And now let me make some room, and let's do some other operations. Next up is dividing rational expressions. The rule for dividing fractions says to keep the first fraction exactly the same, change the division operation to multiplication, and flip the second fraction, write its reciprocal. And now this is just like a multiplication question. Before actually multiplying these rational expressions, we should check if anything is factorable. I can common factor 2x squared minus 8x. I can common factor out a 2x. This quadratic can factor to x minus 5 times x plus 2. And this quadratic can factor to x minus 5 times x minus 4. And now the next thing I want to do is, before canceling any factors, I want to state the restrictions on the variable. So let me make a bit of room so I can write those restrictions. The restrictions are any value of x that would make the original expression undefined. Well, the original expression would be undefined if either of the rational expressions were undefined, and that would happen if either of the denominators were 0. But also, the original division question would be undefined if the value of this fraction was 0, because you can't divide by 0. And that fraction would be 0 if the 4x squared was 0. So to check for restrictions, for a division question, you're going to have to check in these 3 spots. Meaning on the line below, I'll be checking for restrictions in all 3 of these spots. So any value of x that makes any of these factors be 0 is a restriction on the variable, which means x cannot equal 5, -2, 0, 5 again, or 4. And now that the restrictions are stated, I can start canceling factors. Any factor that's in a numerator in either of the fractions can be canceled if the same factor is in the denominator of either of the fractions. So these factors of x minus 5 can be canceled. This factor of x can be canceled with one of those 2 factors of x. And this 2 over 4 can be reduced to a half. And now I can multiply the fractions. I have x minus 4 times another x minus 4, which I could just write as x minus 4 squared. And that's all divided by x plus 2 times 2x. And then once again, I'll have to restate those restrictions on the variable. And now I'll make some room so we can do an example where we add or subtract rational expressions. In this example, we have 2 rational expressions being added. When adding rational expressions, you need a common denominator if we're going to combine and simplify them. But before trying to get a common denominator, a good first step is to check if anything is factorable. I notice I have this quadratic trinomial. It would factor to x minus 8 times x minus 1. Now that the denominators are in factored form, it's easy to see the restrictions on the variable. X can't be 8, or 1, or 8 again. If x was either 8 or 1, it would make the sum of these rational expressions undefined because division by 0 is undefined. So I'll state those restrictions. And now I'll go ahead and try and get a common denominator. I notice this denominator is a product of x minus 8 and x minus 1, while this denominator just has a factor of x minus 8. So if I multiplied this fraction top and bottom by x minus 1, I would then have a common denominator. And now that these denominators are the exact same, I can combine these into a single fraction by keeping that common denominator and adding their numerators. And then all that's left to do is simplify the numerator. I'll distribute the 2 into the x minus 1. And if I collect my like terms, x plus 2x is 3x. And there's the final simplified answer with the restrictions. Must know number 3, vertical asymptotes. Now that we know how to simplify and state restrictions on rational expressions, we can start talking about the properties of their graphs. The first main property that a lot of rational expressions have are vertical asymptotes. If a function, let's call it f of x, has a vertical asymptote at x equals a, 3 things would be true. Number 1, the value of the function at a, so f at a, would equal some non-zero number divided by 0, which would make the original function undefined at that x value of a. And number 2, the limit of the function as the x value approaches a would be either positive or negative infinity. As a function approaches a vertical asymptote, it always goes towards infinity or negative infinity. And that's because, number 3, the graph will always just approach the vertical asymptote, but it'll never touch it or cross it. So let me make some room and let's look at an example of a function that has 2 different vertical asymptotes. Looking at this rational function, let's try and figure out where the vertical asymptotes are, and then also I'll show you its graph and we'll look at its one-sided limits. To know where its vertical asymptotes are, what I'll start by doing is looking at the restrictions of this function. So I'll try and find what values of x make this denominator 0. And I would be able to see those more easily if I put it into factored form. The numbers that multiply to -8 and add to -2 are -4 and 2. So I can factor that quadratic in the denominator to x minus 4 times x plus 2. And now I can more easily see what values of x make this function undefined. It would be undefined if either of the factors in the denominator were 0. So it'll be undefined if x is either -2 or 4. Now restrictions on the variable do always result in a discontinuity of the graph, but it's not always a vertical asymptote. To verify that there are vertical asymptotes at x equals -2 and x equals 4, I'll show you that when subbing those values into our function, we get a non-zero number over 0. F at -2 is 1 over 0, and f at 4 is also 1 over 0. Since both of those x values result in a non-zero number being divided by 0, I know that there's going to be a vertical asymptote at those x values. So there are vertical asymptotes at both x equals -2 and x equals 4. And let me show you what the graph of this function roughly looks like. Notice this function is divided into 3 branches, and that's because of the 2 vertical asymptotes that the function has. Also notice the function has a horizontal asymptote at y equals 0, but I'll explain to you about horizontal asymptotes in the next section. What I want you to notice before moving on is that the function never touches or crosses these 2 vertical asymptotes. As it approaches those vertical asymptotes, the function either goes up towards infinity or down towards negative infinity. So if I were to record the one-sided limits of this function as it approaches the vertical asymptotes, the limit of the function as x approaches negative 2 from the left, well, from the left of negative 2, as the function approaches negative 2, it goes up towards infinity. But as the function approaches negative 2 from the right of negative 2, it goes down towards negative infinity. And then as it approaches this vertical asymptote of 4 from the left of 4, it goes down towards negative infinity. But as x approaches 4 from the right of 4, the function goes up towards positive infinity. Notice the limits of the function as x approaches a vertical asymptote are all either infinity or negative infinity. That's always what happens as you approach a vertical asymptote. And that's why these vertical asymptotes are often called infinite discontinuities. Must know number 4, horizontal asymptotes. Not only can rational functions have vertical asymptotes, but they also sometimes have horizontal asymptotes. The rational function f of x has a horizontal asymptote at the line y equals b if the limit of f of x as x approaches infinity and or negative infinity is equal to b. So basically at the extremes, if the y values of the function trend towards a specific finite value, there's a horizontal asymptote at y equals that finite value. And now let's look at 2 types of rational functions that have horizontal asymptotes, and I'll show you how to calculate where those horizontal asymptotes are. The first type of rational function that has a horizontal asymptote is the type where the degree of the function in the denominator is greater than the degree of the function in the numerator. When that happens, it's guaranteed that there's going to be a horizontal asymptote at the line y equals 0. And let's take a look at an example of a function where that's the case, and I'll show you why the horizontal asymptote is at y equals 0. So here I have a rational function where the function in the numerator is degree 1 and the function in the denominator is degree 2. Since the function in the denominator is a higher degree than the function in the numerator, there's going to be a horizontal asymptote at y equals 0. But let me actually show you why it's at y equals 0 by finding the limit of the function as x approaches infinity. Now, to see what happens to this function as x approaches infinity, there's actually a trick for rewriting it. You find the highest power of x that's in the denominator, and you actually divide all of the terms by that highest power of x. Or algebraically, what's really happening is we are multiplying this expression by 1 over the highest power of x, top and bottom. So really, we're just multiplying the expression by 1, which doesn't change its value, but it'll be written in a different format, which will be easier to find the limit of. So I'll be finding the limit, as x goes to infinity, of this function with all of its terms being divided by x squared. And now when finding the limit of this rational function as x goes to infinity, I can just find the limit of each individual term as x goes to infinity. Well, as x goes to infinity, all of these 4 terms are going to approach 0, leaving me with 0 over 1. So that limit will just be equal to 0 over 1, which is just equal to 0, which is why there's a horizontal asymptote at the line y equals 0. But you don't have to go through this whole limit calculation every time you want to find the horizontal asymptote. Just check. If the function in the denominator is a higher degree than the function in the numerator, you know there's going to be a horizontal asymptote at the line y equals 0. But what about case 2? What if the degree of the numerator is equal to the degree of the denominator? Well, when that happens, the horizontal asymptote is actually at the quotient of the leading coefficients. So for example, this function, because the numerator is a degree 1 polynomial and the denominator is also a degree 1 polynomial, since their degrees are equal to each other, the horizontal asymptote is going to be at the quotient of their leading coefficients. The leading coefficient of the function in the numerator is 3, and the leading coefficient of the function in the denominator is 1. So the horizontal asymptote would be at the line y equals 3 divided by 1, which is just 3. But let me show you the limit at infinity so you can see why it's at y equals 3. When finding the limit of f of x as x approaches infinity, I could once again rewrite this function by dividing all of the terms by the highest power of x that's in the denominator. There's an x to the 1 in the denominator, so I'll divide all the terms by x. And as these x's approach infinity, the value of these fractions are going to be approaching 0, leaving me just with 3 divided by 1, which is equal to 3, which is why there's a horizontal asymptote at the line y equals 3. And then let's actually take a look at the graph of this function. When looking at the graph of that function, notice that as x approaches infinity, so as you move forever to the right, the y values of the function approach 3. And in fact, as x approaches negative infinity, the y values approach 3 as well. So that's what happens when you have a horizontal asymptote at the extremes. As x approaches infinity and or negative infinity, you'll see the function approaching a finite y value. And in this case, the y values are approaching 3. Now, I should also mention that a function only approaches its horizontal asymptote at the extremes. So that means for some finite value of x, the function actually can touch or cross its horizontal asymptote, unlike vertical asymptotes that functions can never touch or cross. Must know number 5. Slant asymptotes. Not all rational functions have horizontal asymptotes. Some of them have what are called slant or oblique asymptotes. So for some rational function f of x that is a quotient of two functions of x, if the degree of the function in the numerator, p of x, is 1 greater than the degree of the function in the denominator, q of x, then that means there is an oblique or slant asymptote. So let's take a look at a rational function where the degree of the function in the numerator is 1 degree higher than the function in the denominator. Notice the numerator is degree 2, while the denominator is 1 degree less, it's degree 1. When that's the case, there's a slant asymptote. Now, when finding the equation of a horizontal asymptote, I showed you that we can just find the limit as the function approaches infinity. But if we tried to do that for this function, we would see that it doesn't have a limit. As x goes to infinity, y goes to infinity as well. But even though it doesn't go towards a specific finite value, it does actually grow along a linear path. And we can find the equation of that line that it grows more closely towards, called the slant asymptote, by performing the polynomial division and then analyzing its limit. So let me go ahead and actually divide the numerator by the denominator. And I can do that using any division method. I'll use synthetic division. For synthetic division, I write the 0 of the divisor up here. And then the coefficients of the dividend, 1, 4, and 10, go across the top of my table. Then I can bring the 1 down. 2 times 1 is 2. Add the column to get 6. And then just keep repeating the process. And that answer tells me that when I do x squared plus 4x plus 10 divided by x minus 2, the quotient is 1x plus 6 with a remainder of 22. So I can rewrite this in quotient form. It's equal to 1x plus 6 plus the remainder 22 over the divisor of x minus 2. And now you can see how this function grows as x goes to infinity. As x goes to infinity, this fraction is going to go towards 0. So the y values are going to go towards infinity along this line, x plus 6. Which makes this quotient, x plus 6, the equation of the slant asymptote. And now let me show you what the graph of this function looks like. And also notice it's going to have a vertical asymptote at x equals 2 because the denominator of the function is 0 when x is 2. So here's a graph of the function. Notice it has a vertical asymptote at x equals 2, but that diagonal line is the slant asymptote, y equals x plus 6. And as x goes to infinity or negative infinity, notice that the function keeps getting closer and closer and closer to that line y equals x plus 6. Must know number 6. Holes. Earlier I showed you that division by 0 causes a discontinuity in the graph of a rational function. It can cause a vertical asymptote, or in this section I'll show you how it can actually cause a hole in the graph of a rational function. F of x has a hole at x equals a if f at a is the undefined expression 0 divided by 0. To show you how we can tell when a rational function has a vertical asymptote versus when a restriction is going to cause a hole, let's take a look at this function. To find the restrictions on this rational function, we should start by factoring it. I notice the numerator is a difference of squares, so I can factor it to x minus 2 times x plus 2. And the quadratic in the denominator, the numbers that multiply to 2 and add to negative 3 are negative 2 and negative 1. So I can factor it to x minus 2 times x minus 1. And now I can more easily see what the restrictions on x are. Since division by 0 is undefined, whatever values of x make this denominator be 0 would be restrictions on the variable, causing discontinuities in the graph of the function. Well, the denominator would be 0 if either of these factors were 0. So the restrictions on x are that x can't be 2 or 1. And these restrictions, graphically, will either result in a vertical asymptote, called an infinite discontinuity, or a hole in the graph, called a removable discontinuity. And how we could tell is by subbing both of these values into our rational function and analyzing the result. Let me start by seeing what undefined expression I get when I sub in 1 for x. The numerator becomes negative 3 and the denominator becomes 0. Now this expression is undefined, but because the numerator is a non-zero number and the denominator is 0, I know that that's going to cause a vertical asymptote at x equals 1. And now let's check what happens when I sub in 2 into the rational function. If I sub in 2, I notice that it'll make both the numerator and the denominator be 0. And when you get 0 over 0, that's going to cause a hole in the graph at the point where x is 2. Now I don't know what the y-coordinate of this hole is quite yet, but after I simplify this expression by canceling these factors of x minus 2 that create the hole in the graph, I get a new function that is actually defined when x is 2. So I could sub 2 into the simplified version, and when I do that, I would get the y-coordinate of the hole. Now I know here in our restrictions it says x can't equal 2, that's why we're allowed to say that this function is actually equal to the one above by stating this restriction. But if we ignore the restriction and actually sub 2 into the function, it does give us the y-coordinate of the hole. So I'll make a note of that. To find the location of the hole, sub x equals 2 into the simplified equation. And if I sub 2 into this function, I would get 4 over 1, which is 4. So I know the y-coordinate of the hole is going to be at 4. Now let me quickly show you what the graph of this function looks like. Notice the function has a vertical asymptote, an infinite discontinuity at x equals 1, and it also has a hole in the graph at the point where x equals 2. That's the removable discontinuity. And the reason why it's called a removable discontinuity is because if we look at the rational function that we have here, the factor that creates the discontinuity at 2, this factor of x minus 2 in the denominator, we are able to cancel out that factor, so remove that factor that creates the hole, to get a simplified expression that tells us the location of the hole. And also because the degree of the numerator and denominator are equal to each other, they're both degree 2, there's a horizontal asymptote at y equals the quotient of the leading coefficients, 1 divided by 1, which is why there's a horizontal asymptote at y equals 1. And also I want to point out the limits of this function as they approach the restrictions on x. As the function approaches x equals 1 from the left, it goes down to negative infinity, and from the right, it goes up to positive infinity. That's always what happens as you approach a vertical asymptote. But what happens as the function approaches an x value of 2 is the function approaches the finite value of 4, which the hole is at. And we could have actually calculated that finite value of 4 using limits. To find the limit of this function as x approaches 2, I could find the limit of this simplified version of the function as x approaches 2. Those limits would be equal because the functions are equal to each other at all x values as long as x is not equal to 2. Must know number 7, the x and y intercepts of a rational function. Let me show you the methods for calculating both the x and y intercepts of a rational function. F of x has an x-intercept at x equals a if f at a equals 0. So that just means the x-intercept of the function is just at whatever x value makes the y-coordinate be 0. And for the y-intercept of a rational function, f of x has a y-intercept at y equals f of 0. So that just means whatever the y value is, when you set x to 0, that's the y-intercept of the function. So let's look at an example of a rational function where we'll calculate both the x and y-intercepts of the function. For this rational function, let me start by finding its x-intercept. To find the x-intercept, I just have to find whatever x value makes the function have a y-coordinate of 0. So I'll just set the function's y value to 0 and then solve for x. And before solving, I should note the restriction on the function. Notice that x cannot equal 2. That would make the denominator 0, and division by 0 is undefined. What makes a rational function be 0 is if the numerator is 0. So I can just set the numerator equal to 0. And then solving that equation, I see that if x was negative 4, this function would be 0 over negative 6, which is 0. So there's an x-intercept at the point negative 4, 0. And now let me calculate the y-intercept. The y-intercept is at whatever y value you get when you set x to 0. So I'll just evaluate f at 0. Subbing in 0 for these x's, I get 4 over negative 2, which is negative 2. So my y-intercept is at the point 0, negative 2. And before showing you the graph of this function, let's quickly make a note about the asymptotes of this function. Because the numerator and denominator are both degree 1, they're equal degree, the horizontal asymptote will be at the quotient of their leading coefficients. 1 divided by 1 is 1. So there will be a horizontal asymptote at the line y equals 1. And there'll be a vertical asymptote at x equals whatever the restriction on x is. X cannot equal 2. Subbing 2 into this function gives me 6 over 0. A non-zero number over 0 is a vertical asymptote. So vertical asymptote at the line x equals 2. And now looking at this graph, we'll see those asymptotes, and we also see the x-intercept of negative 4 and the y-intercept of negative 2. Must know number 8, graphing reciprocal functions. Let me start by quickly summarizing some properties of reciprocal functions. If we have the function g of x, which is equal to the reciprocal of the function f of x, so if it equals 1 over f of x, there are a few things we should know about how this function in the denominator relates to the reciprocal function g of x. First of all, whatever makes f of x 0 is going to make g of x undefined, because division by 0 is undefined. And whatever makes f of x be 0 would be considered the x-intercept of f of x. So the x-intercepts of f at x are equal to the vertical asymptotes of g of x. And since g of x is just the reciprocal of f of x, the reciprocal of a function doesn't change its sign. So whenever f of x is positive, 1 over f of x, g of x, will also be positive. And same if f of x is negative, g of x will also be negative. And next, whenever the f of x value is increasing, whenever it's getting bigger, the value of g of x is going to be getting smaller. Because when the denominator of a fraction gets bigger, the overall value of the fraction gets smaller. So the intervals of when f of x and g of x are increasing or decreasing are actually opposites of each other. Because the numerator of g of x is degree 0, our denominator is going to be higher than degree 0, creating a horizontal asymptote at y equals 0. And the last thing I want to mention, whenever f of x is at a local max, g of x will be at a local min. And whenever f of x is at a local min, g of x will be at a local max. And now let me make a bit of room so we can graph a few reciprocal functions. Let me start with the reciprocal of a linear function. Our function f of x is the reciprocal of a linear function. The linear function is x minus 3. When graphing this function, I think it's best if we start by analyzing the key properties of the function that's in the denominator. So let's just look at the function x minus 3 to start with. One of the key things I'm interested in is, what is the x-intercept of this function, right? What makes it be 0? Well, this would be 0 if x was 3, so it has an x-intercept at the point 3, 0. So if I were to make a table of values for this linear function, I would put 3 in the middle, and then choose a couple points to the left and a couple points to the right. And then subbing these x values into this linear function, I could calculate the corresponding y values. And now using these properties and these points, I can try and figure out what the graph of the reciprocal of x minus 3 looks like. Well, remember, reciprocal functions always have horizontal asymptotes at y equals 0, and there's going to be a vertical asymptote at whatever value of x makes the function in the denominator be 0. And I recorded that over here. At an x value of 3, the function in the denominator is 0. So there will be a vertical asymptote at x equals 3. And now let me get some points for this rational function. I'll choose the same x values that I chose for the x minus 3 function. But notice f of x is equal to 1 divided by x minus 3. So if these are the y values for x minus 3, my reciprocal function, I would have to do 1 divided by each of those values. And this would be enough information to sketch a pretty accurate graph of the reciprocal function. On that grid, I think I'll actually graph the function x minus 3 as well. So I'll do that to start with. Plotting these points, I get that linear function x minus 3. And then for the reciprocal function f of x, I could graph the asymptotes. And then I could roughly plot these points. And then I could connect those points using the proper behavior I know the function's going to exhibit. As x goes to infinity or negative infinity, I know it's going to be approaching that horizontal asymptote. And as the x values approach the vertical asymptote, the function's going to be going either down to negative infinity or up to positive infinity. And then hopefully this graph allows you to see all of these properties we have over here. F of x is increasing over its entire domain, which is why 1 over f of x is decreasing over its entire domain. And whenever f of x is negative, the reciprocal is also negative. And whenever f of x is positive, the reciprocal is also positive. And the x-intercept of the f of x function makes the reciprocal become 1 over 0, which is undefined, which creates this vertical asymptote. And now let me shrink this work and let me show you what some reciprocal quadratic functions could look like. For reciprocal quadratic functions, there are 3 general shapes they could make. Instead of giving you equations and coming up with tables of values and sketching them very accurately, let's just use these properties to figure out what the graphs of reciprocal quadratics could look like. Well, remember, quadratic functions can have either 0, 1, or 2 x-intercepts, and that's what's going to cause the different shapes for the reciprocal functions. Let me start by sketching a quadratic with 2 x-intercepts. If I zoom in on this quadratic that has 2 x-intercepts, let's call this function f of x, and let's graph its reciprocal, 1 over f of x. Well, I know reciprocal functions have horizontal asymptotes at y equals 0, and whenever f of x has an x-intercept, so whenever its y value is 0, the value of the reciprocal function will be 1 over 0, which is undefined and creates a vertical asymptote. And now to graph the branches of the reciprocal function, I have to keep some properties in mind. I know it's going to approach the horizontal asymptote at the extremes, and I know as it approaches the vertical asymptote, it's either going to go up to infinity or down to negative infinity. Notice to the left of the first vertical asymptote, f of x is positive, so the reciprocal function will also be positive, meaning it will look something like this. And same thing to the right of the second vertical asymptote, f of x is positive, so its reciprocal will also be positive. And also notice in those 2 sections, when f of x is decreasing, the reciprocal is increasing. And when f of x is increasing, the reciprocal is decreasing. And now let's look between the vertical asymptotes. This section is negative, meaning the reciprocal will also be negative. And since f of x has a local min right there, the reciprocal will have a local max at that same x value, making this branch of the function look like this. And now let's see what happens if the quadratic only has 1 x-intercept. If this is our f of x function, and we want to graph 1 over f of x, once again, reciprocal functions have horizontal asymptotes at y equals 0, but there's only one place where f of x is 0, meaning there's only one place where 1 over f of x is 1 over 0, which is undefined, so there's only one vertical asymptote. And now to the left of the vertical asymptote, f of x is positive and decreasing, so the reciprocal will still be positive, but it will be increasing. And to the right of the vertical asymptote, f of x is still positive, but increasing, so the reciprocal function 1 over f of x will be positive, but decreasing. And now let's do one more where the quadratic, the third scenario, has no x-intercepts. If this is our f of x function, notice it has no x-intercepts, which means there are going to be no vertical asymptotes. But it still will have a horizontal asymptote at the line y equals 0. And because this function is always positive, the reciprocal will always be positive. And when this function is decreasing, the reciprocal will be increasing. And then when this function switches to increasing, the reciprocal will switch to decreasing. And because I see there's a local min here, at that same x value is where there's going to be a local max for the reciprocal, making it look like this. And there's our reciprocal of f of x. So there you have it. Hopefully you understand the connection between a function and the graph of its reciprocal. Must know number 9, solving rational equations. When solving a rational equation, you should always start by stating the restrictions. That way you can make sure they're excluded from the solution set. And then, before trying to solve, you can eliminate any fractions by multiplying both sides of the equation by the lowest common denominator. And then after eliminating the fractions, you can just go ahead and use your algebra skills to solve the equation. So let's look at a few different examples. In this first example, we need to solve for what value of x makes this equation true. I can get rid of these fractions if I multiply both sides of the equation by the lowest common denominator between these denominators here. And since both the denominators are x, their lowest common denominator is of course x. So all I would have to do is multiply both sides of this equation by x. I can then distribute the x to both terms on the left side of the equation, and then all of the fractions should simplify, leaving me with, on the left side of the equation, just 3 plus 2x, and on the right side, just 5. And then you can just rearrange this equation to solve for x. I'd have 2x equals 5 minus 3, which is 2, which means x is equal to 1. And then don't forget, anytime you solve an equation, you should check the final answer in the original equation to make sure it's true. 3 over 1 plus 2 is 5. Now let's try a second example. In this equation, I have two fractions. If I look at their denominators, they're x minus 1 and x. The lowest common denominator between those two denominators would just be the product of them. So x times x minus 1 will be my lowest common denominator. That means I should multiply both sides of this equation by x times x minus 1. And on the left, I'll distribute that product to all three terms that are on the left side of the equation. And on the right, the product of those three factors will just be 0. And now all the fractions should simplify nicely. Looking at the first term, I can cancel these factors of x minus 1. And the third term, I can cancel these factors of x, so there are no more fractions left. I've got x times 3 plus 5x times x minus 1. I'll distribute that 5x plus x minus 1 times 2. I'll distribute that 2 to the x minus 1. And now I just have a quadratic equation to solve. It's 5x squared, and then 3x plus 2x is 5x, minus 5x is 0x, and then minus 2. So I have 5x squared minus 2 equals 0. When you have a single term with a variable, we can just rearrange it to isolate the variable. I would have x squared equals 2/5, which means x equals plus or minus the square root of 2 over 5. So those would be my answers to the original equation. And for both of the equations we just solved, I forgot to mention the restrictions on the variable. In the first equation, the only restriction was that x can't be 0, and the solution was 1, so that's fine. And in the second equation, the restrictions would be x can't be 1, and x can't be 0. Must know number 10, solving rational inequalities. Here are the steps for solving a rational inequality. Step 1, move all terms to one side. Step 2, combine expressions to make a single rational expression. Step 3, find the x-intercepts and the restrictions of the function. And then step 4, use those numbers to divide the function into intervals. And then lastly, test a value within each interval to see if it satisfies the inequality. And let me make some room and let's go ahead and solve a rational inequality. When solving this inequality, the first thing I should do is move all the terms to one side. So I think what I'll do is I'll take this term and bring it to the left by subtracting it. And now I need to combine these expressions by getting a common denominator. And my common denominator will just be the product of these denominators. So this fraction will be multiplied by x minus 3 top and bottom, and this fraction will be multiplied by x plus 1 top and bottom. And now notice these denominators are the same, so I can combine these two fractions into a single fraction by keeping that common denominator. And then in the numerator, I have x minus 3 times x plus 3, which is x squared minus 9, minus the product of x minus 2 and x plus 1. I'll make sure to put that product in brackets, and it's x squared minus x minus 2. And then in the numerator, I would have to subtract all three of the terms that are in brackets, and then collect my like terms. When doing that, the numerator will simplify to x squared minus x squared is 0. I've got minus a negative x, that's x, and negative 9 minus negative 2, that's negative 7. Now to figure out when this function is greater than or equal to 0, I'm basically trying to figure out when is it above the x-axis. So I'm going to divide it into intervals based on where its x-intercept is and its vertical asymptotes are, because I know those are the places where the function might switch from being above 0 to being below 0. So remember, its x-intercept will be at an x value that makes the numerator be 0, so there'll be an x-intercept at 7, and the vertical asymptotes will happen at the restrictions of the variable. Since division by 0 is undefined, whatever makes the denominator be 0 is a restriction, so x can't be 3 or -1. And now I have to divide the function into intervals based on these values. So what I'll do is I'll actually make a chart where I'm going to do testing of values in the intervals I create. I call it a sign chart or a factor table. Here's what it looks like. Notice I've arranged the x-intercepts and restrictions in ascending order at the top here. And I always start with -infinity and end with +infinity. And now what I want to do is choose a test value within each of the intervals I've created. So between -infinity and -1, I need a test value. Any number in that interval will do, so I'll choose -2. And then the next interval is from -1 to 3. I'll choose a test value of 0. And then between 3 and 7, I'll choose 5. And from 7 to infinity, I'll choose 10. And now what I want to do is basically figure out, is this function positive or negative in each of those intervals? So I'll take these test values that I chose, and I'll sub them into this function. And the way I've created this table allows you to do it in an organized way, which makes the calculation easy. I'm just going to sub it into each of these three factors that make up the rational function, and not even record the answer, but just whether it's going to be positive or negative. So when x is -2, it makes all three of those factors be negative, which means we would have a negative divided by a negative times a negative. That's a negative over a positive, which means the overall sign of the function will be negative. If you have an odd number of negative factors, the overall sign will be negative. And an even number of negative factors, the overall sign will be positive. And knowing the overall sign of the function is helpful in answering the inequality because we're just interested in when is it greater than or equal to 0. So that means when is it positive? Well, in the first interval, it's negative. But after we move across this vertical asymptote, looking within the next interval, my test value is 0. When I sub that into these factors, 0 minus 7 is negative, 0 minus 3 is negative, but 0 plus 1 is positive. Because I have an even number of negative signs, that's going to be a positive result, which means this function is positive, which is greater than or equal to 0. So this interval from -1 to 3 will be part of my final answer. And then for the test value of 5, I get negative, positive, positive when I sub them into those factors. One negative sign will give a negative result. And then subbing in 10, I get positive, 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 which is a positive result. So since I want to know when is the function greater than or equal to 0, the intervals where the function has an overall positive sign, so between -1 and 3, and between 7 and infinity, are going to be my answers to this inequality. So I'll say my answer is that the inequality is true when x is an element of numbers within this first interval between -1 and 3, or if x is between 7 and infinity. And notice, because the original inequality wants to know when it's greater than or equal to 0, I do want to include the x-intercept in my answer, which is why I put a square bracket at 7. But I made sure to put round brackets at my restrictions because the function doesn't even exist there, so they can't be part of my final answer. And it might be good to end the video by making a quick sketch of the graph of the rational function we are working with so you can see how this is the answer to the inequality. So I'll make a bit of room. And this is the function we're working with here. We know it has an x-intercept of 7 and these two vertical asymptotes at -1 and 3. And because the function in the denominator is higher degree than the function in the numerator, there'll be a horizontal asymptote at y equals 0. And also there's an x-intercept at 7, which means this function actually touches and goes through the horizontal asymptote. So what this chart showed me is that between -infinity and -1, the function is negative, which means it must be down here. And then between -1 and 3, the function's positive, so it must be up here. And then from 3 to 7, the function's negative. And then from 7 to infinity, the function is positive. So it's above the x-axis, but it does have to start approaching the horizontal asymptote. So there's a rough sketch of the function. And notice how it shows that this is the answer for when the function is greater than or equal to 0. Hopefully this video helped you understand rational functions. Let me know in the comments what you want a top 10 of next.
Jensen